Now that we've had a look at the transitive closure and actually found some ways of finding the transitive closure of given relations, we're going to take a look at something called Warshall's algorithm, which is a much more efficient way of finding the transitive closure of a relation. So the first thing we're going to do is just review the definition of transitive closure and review the methods that we use to determine transitive closures of relations already. We're going to describe what Warshall's algorithm is, and then we're going to use it on an example to show how much nicer and cleaner it is to use than some of the other ones. So suppose we have a relation R on a set A, and this could be literally any relation. The transitive closure of R, that's written R plus, that is a transitive relation that has the smallest number of ordered pairs, but that also includes all the ordered pairs from the original relation R. Another way of saying that is it's the smallest transitive relation that contains R. So we've had a couple of ways of determining the transitive closure of a given relation. The first one is we take our directed graph representation and look for paths that have length 2. We didn't really describe it like this last time, but what I mean by paths of length 2 looks like this. We have two arrows, one from A to another element B, one from B to another element C, and then we make sure that we draw in the arrow A to C if necessary. If the arrow from A to C is already there, we don't have to draw it again. We just have to draw it in there if it's not there already. And then we check out what we have. We check to see if it's transitive. If it is, we're done. If not, we go do this exact same process again with our new arrows. So, and then we had an alternate method of finding the transitive closure, and that is the whole thing where we were looking at elements or things in the set that were downstream from one another. So let me just remind you, our theorem was let R be a relation on the set A, then R plus is the set of all ordered pairs A, B, and again, A points to B, where A is upstream from B or B is downstream from A. And the way we can see this is it's connected by a directed path in R, and a visual of this is, all that means is we connect A to B, we draw an arrow from A to B whenever we have this picture, where A is pointing to a vertex, or A is pointing to an element, that element is pointing to another element, and we keep on moving down the arrows in the correct direction until we get to B. So anytime we have that picture there, we have to draw an arrow from A to B. So we can look at all the directed paths of R and then draw the appropriate arrows from that as an alternative. So I want to say a couple things about the above algorithms, because always, even as computer scientists, whenever you have an algorithm, there are some things that are important for you to look at those algorithms in terms of implementing them. So as a strength, the algorithms are very thorough. They make sure that we get all the arrows that we need to make it a transitive make it have the transitive property. We consider all possibilities, all the ways that can go wrong. It always gives us an accurate outcome. The weakness is that they're pretty inefficient. A lot of times, for instance, if we have a lot of the paths we look at where A points to B points to C, we already have an arrow where A points to C. And so we do a lot of searching in places where we really don't need to. So from the point of view of an algorithm, this will make a long runtime for the algorithm. So we'd like to make them a little more efficient. So we're going to introduce Warshall's algorithm, which gives us the thoroughness we need to get all the arrows that we need to make it transitive, but also gets rid of some of the redundancy in some of our other algorithms, so it has a faster runtime. All right, so here's how the Warshall's algorithm works. So we take the elements of our set, we put them in order, any order that we want. We just take them, we line them up from left to right or whatever, and then on the left are the first ones, on the right are the second ones. Or if you like lining them up right to left, I'm not going to stop you, but just make sure you put them in order. So here's what we're doing. So we'll take our set A, A1 is the first one, A2 is the second one, etc. AN is the last one. It does not matter what order you put them in, any order will work. And that's a good thing too, right? Because we don't want to have to say, well, here's your set, good luck finding the right order. So now we're going to look for all the paths of length 2 where A1 is in the middle. So we're looking for one of the AIs points to A1 and A1 points to one of the AJs. And then what we do is, well, this isn't going to be, this is very intuitive. We're just going to draw the arrow between A and I to AJ if it hasn't been drawn already. Next step is we're going to do exactly the same thing to A2, right? We're going to go to A2, find all the paths of length 2 where A2 is in the middle. We're going to have AI to A2 to AJ, and then draw all the arrows between those AIs and AJs for length 2, and we're going to keep on going for the rest of them. And we're going to do the same for A3, the same for A4, all the way out to AN. So at the kth iteration of the algorithm, we're going to look at AK in the middle, and we're going to look at all AI pointing to AK and all elements that AK points to AJ, and then we're going to draw the arrow AI to AJ for all those. So for the early elements of A, we don't really check very many paths. We only check the paths through them once, right? And then it seems like, well, we never come back to see if we got all the arrows through there to work all right. So it might seem like we've left something out, but it turns out this does not happen. And let's see actually how this works on the example that we were looking at before. I have a low battery here. Pardon me. All right, so we are going to consider the following relation. This is the one we saw before, the one we saw on the last video. All right, so, hey, battery's charging now. Good. So we're going to use Warshall's algorithm on this particular relation. We want to get a transitive closure. So first of all, I'm going to make a boring order. We could put these elements 1, 2, 3, 4, 5 in any order we want. I'm going to put them in the boring order, just numerical order, because, well, let's face it, I'm a boring person. So 1 first, then 2, then 3, then 4, and then 5. All right, so I'm going to look at 1 first, and nothing exciting happens with 1, because remember, we're looking at all the paths where 1 is in the middle. So something points to 1, and then 1 points to something, but, well, nothing's pointing to 1, so there's nothing we can do. So that's not so exciting. For 2, we have a lot going on, right? Because for 2, we have 1 pointing to 2, and 2 pointing to 4, right? And we have 3 pointing to 2, and 2 pointing to 4. That means in this part of the algorithm, we add in the arrow 1 to 4 and then 3 to 4. So there we have it. For 3, there's nothing for 3 because remember, 3 would have to be in the middle of our path. So we'd have to have something pointing to 3 and then 3 pointing to something. But again, nothing's pointing at 3, so we do nothing. Now for 4, we have tons of stuff going on because we have 1 pointing to 4 and 4 pointing to 5. We have 2 pointing to 4 and 4 pointing to 5. We have 3 pointing to 4 and 4 pointing to 5. So we have to add in the arrows 1 to 5, 2 to 5, and 3 to 5 to fill those in. And there they are. And then we get to 5. Well, 5 has a similar problem as 1 and 3, kind of the opposite problem, right? Because we have a bunch of arrows pointing at 5. Unfortunately, 5 isn't pointing at anybody, so there's no there are no paths where 5 is in the middle. So again, we do nothing, and notice that we got all the arrows for the transitive closure, all the ones that we did before. If you look at all the arrows downstream from any particular vertex, it's pointing at all of those. So you may have thought that, well, what happens if we use a slightly more exciting order? This is about as exciting as my life gets. We're going to use the order. We're going to do 4 first, then 3, then 2, then 5, then 1, and see if anything different happens. All right, so if we're looking at 4, things are happening all at once. Actually, not much is happening, right? Because the only one pointing at 4 is 2, and the only one that 4 points at is 5, and so the only one in the middle is 2 to 4 to 5. So we have to add the arrow from 2 to 5. There we go. First step, not much going on. For number 3, again, same deal. No paths where 3 is in the middle, and so we can't do anything. Nothing's pointing at 3, so we're stuck. So that's a bummer. For 2, though, we have tons of stuff going on, right? We have 1 to 2 to 4, right? We have 1 to 2 to 5, and then we have 3 to 2 to 4, and 3 to 2 to 5, and that means that's 4 arrows that we have to add. 1 going to 4, 1 going to 5, 3 going to 4, and 3 going to 5, and there they are. Well, that's a lot of arrows. Let me see. What comes after 2? Oh, 5 comes after 2. And once again, 5, we can't do anything because all we have is arrows pointing at 5. And so 5 can't be in the middle of anything because it's not pointing at anything. And 1, we can't do anything either because even though one is pointing at things, nothing is pointing at one, so we can't have one in the middle of a path of length 2. So actually, we're done, right? And even though we're done and it seems like, oh no, we're in trouble, no, we're not in trouble. We got all the same arrows that we got before. We got the same transitive closure as when we did it in the other order. So still got all the arrows for R+. All right, so now that you've seen Warshall's algorithm in action twice, you should be able to work on the activities that are on the PDF. The file is called Warshall's algorithm.